what our scope was is that we had 3 different subsystems. One was the turocopter, one was the thermocopter, the other one was the Gets UI. What we had for the thermocopter was it would fly around and map hotspots, and then that would send the communications to the Gets UI, which would then send those coordinates back to the turocopter, and the turocopter would fly to that coordinate and spray fire retardant onto the areas that were hot.
A project in response to help to save many lives when it comes to firefighters. In the end of the first semester, we were notified by our sponsor, Professor Abir Bastava, that he wants us to participate in the EOH, or the Engineering Open House.
What the engineering open house is that kids would come on a campus and we would have to provide interactive activities that would get kids interested into science and engineering. So the 2 activities that we chose was a temperature sensing activity and a turret targeting activity. What the temperature targeting activity is that we have 3 different pots, and the kids would have a thermopile which had a thermal array on there. They would go up to each pot and decide which one was hot. And after they decide which one was hot, they would swing around to the turret, and upon button press, the turret would oscillate. And then once they pressed the button, the turret would stop, and we would shoot. And if they would hit the paper targets that would have aligned with the pots, they would win a prize. Since the EOH took about roughly half the semester, we only had the last half in order to implement our 3 subsystem architecture. And with talking to our sponsor and considering time limits and hiccups to our hardware and just a misjudgment of difficulty, we decided to focus on just true stable flight communication with the Gets UI.
At first, we started with a 1-tier architecture with just one board used for pulling of all the sensor data, and then we would do all these computations to get the actual motor speeds that we would need, and then it would send it out directly to the motors themselves, and then the motors would spin at their correct speed.
We noticed when we set up the quadcopter that it tended to overcompensate. We set it up on an axis tester so we could just test one axis, and every single time it would dip down, it would just fly back up and overcompensate, and it would just go back and forth and back and forth.
Talking to the professor about it, we decided to go and change that to a 3-tiered architecture where we'd have a separate board just doing nothing but pulling for sensor data, grabbing sensor data, and working with communication to get the commands through the Wi-Fi machine. Then we would have a computational processor. This goes and takes all of the angles from the communication processor and figures out how much we have to either increase or decrease motor speeds to achieve stability on any axis, and sends this data to the motor control regulator, which does nothing but sends the actual motor speeds to the motor continuously. And with this architecture, we were hoping to cut down on the delays that we were seeing in writing to the motors, but given the amount of handshaking they were having to do, the delays in the end basically matched what we had in the single-tier architecture.
We accomplished a lot of things this semester, one of which was a fully functional GUI that sends commands via Wi-Fi to our quadcopter.
It is a standalone application that runs on any Windows PC. It allows the user to send commands to the quadcopter and monitor statistics about the quadcopter's flight. So with this GUI, the user can see the approximate height the quadcopter is from the ground, as well as the speeds at which each motor is operating at. It also allows the user to launch and land the quadcopter.
You also have the option of choosing the emergency kill button if there are any issues.
In the end, I feel like we could have much better utilized the inertial measurement unit. We should have looked into the accelerometer much earlier than we did. This would have allowed for that predictive control. With this predictive control, I felt that we could have implemented this with only one board and the Wi-Fi shield.
Another thing that we ended up learning is that a bottom-up approach has its downsides. When we got all the individual components working and put them together, we ended up having a lot of issues with timing and communication. We also learned that things take a lot longer than you assume they're going to take. So we learned to prioritize what was the most important thing to the success of our projects and focus on that. We'd like to give special thanks to Professor Shrivastava as well as Dr. Callis, because without them, we wouldn't have been able to make this project possible.